All right, so let's start in on chapter 16. All right, we're going to be discussing a specific class of reactions that we will see for these aromatic compounds, what are called electrophilic aromatic substitution reactions. All right, and so you'll see these abbreviated EAS as well, electrophilic aromatic substitution reactions. All right, so let's sort of pick these apart here. We have our benzene. All right, we're going to be reacting our benzene with some electrophile here. Electrophiles, do they have a lot of electrons or not a lot of electrons? No. So the best electrophiles have this positive charge. If this is our electrophile, what is benzene playing the role of? The nucleophile. All right, and so what we're going to see is a substitution reaction where that electrophile replaces one of the hydrogens on our benzene ring. Okay. We're going to see the same reaction mechanism over and over and over again. We'll change what this electrophile is, but the mechanism remains the same. Again, our benzene ring is playing the role of the nucleophile, so that pi bond in your benzene ring reaches out and attacks that electrophile. Okay. So now I have both my hydrogen as well as my electrophile bound to this benzene ring. And what else am I missing from this intermediate here? Oh, whoops, I'm sorry. There's no positive charge on the E anymore. So what am I missing from my intermediate? A charge. And where does that charge go? All right, we've seen this a bunch. This pair of electrons got taken away from one of those carbons, leaving it with only 6 electrons in its octet. So we have a carbocation on this next door neighbor. Okay. And then the last step is some base is going to come along. We're just going to leave this as generic B here and remove that hydrogen, allowing that pair of electrons to come back down and reform that aromatic ring. Right, so your original pi bond in your benzene ring becomes your new carbon electrophile bond, and that pair of electrons that used to be in that carbon hydrogen bond is now what makes up your new pi bond. Okay, but importantly, in these reactions, you do not break your aromaticity of the benzene ring. That's the whole idea, right? We don't see addition reactions, we instead see these substitution reactions. Okay, so we're going to see a few different ones here where all we're going to do is vary what that E is. Okay. What do we know about benzene though? Stable or not so stable? Nice and stable, right? So it's actually a pretty terrible nucleophile. All right. So in order to have these reactions occur, we need to use really, really good electrophiles. Or what we're going to do is have some catalysts that turn our normal electrophiles into really good electrophiles. All right. So let's take a look at a few of them here. Let me grab my benzene ring again. Cool. All right, so our first few are going to look familiar here. We've got bromine and chlorine. And what we're going to see are these electrophilic aromatic substitution reactions, which adds, or rather substitutes out, one of those hydrogens for our halogen. Okay, but again, you can't just use bromine alone or chlorine alone. You got to sort of have a catalyst in there that'll turn it into one of these really good electrophiles. So you can either use iron or aluminum tribromide. So either iron or aluminum. That's 3 halogens on there. And same thing with the chlorine, either iron with 3 chlorines or aluminum with 3 chlorines. All right, so those are our catalysts for this reaction. Okay, so again, we have this catalyst that's going to convert our bromine into a really good electrophile. So in these reactions, the actual electrophilic species is this complex that occurs between our halogen and our metal halide. Let's just do a specific example. So bromine. Let's just do aluminum. All right, so both of these catalysts are able to accept a pair of electrons from that bromine. Creating this complex here. All right, let's look carefully here. This bromine still just has its 3 lone pairs. What about this one that's attached to the aluminum? How many lone pairs should I put on there? Just 2. And if it's got 2 bonds and 2 lone pairs, what's the formal charge on that bromine? Positive. All right, so we get this halogen aluminum halogen metal complex here. All right, and so this bromine on the very end is our electrophile. All right, and so when that benzene ring comes along and attacks, going to give up that pair of electrons to that bromine with that positive charge. All right, so this halogen forms this complex with this metal that makes it so it's much easier to take that pair of electrons away from that halogen. Makes it a much better electrophile, right? So when we're writing our reagents, we'll see the bromine stacked over the aluminum bromide, but the actual electrophilic species is going to be this complex here. That's the good electrophile that we've created to react with our crappy benzene nucleophile. Okay? And the analogy goes for chlorine as well, right? Very similar. All right. So the next reaction here will create that special compound that we said was going to come up over and over again in this chapter, that special functional group, which has the coolest name of all the functional groups, that nitro group. All right? And so in order to get a nitro group onto your benzene ring, you just have this like absurdly acidic mixture that you use. A combination of both nitric acid and sulfuric acid. All right, and so in this reaction, what happens is the nitric acid will react with the sulfuric acid to produce a small amount of this nitrogen dioxide here. Oops. All right, and let's look at this structure here. What am I missing? That positive charge on that central nitrogen, absolutely. And so this is our electrophilic species. This positively charged nitrogen in the middle here is now really good at accepting a pair of electrons, right? It's in this very polar bond with these two oxygens, leaving it with this positive formal charge. And so that'll make it very easy to accept the pair of electrons. All right, so remember what that nitro group looks like. We sort of abbreviate it as the NO2, but if we're actually going to draw out our structure here, it's double bonded to one oxygen, single bonded to the other. All right, everybody take a second and see if you can't finish off this mechanism here, getting from A to B, now that we have our electrophilic species. All right, so we have our nucleophile being our benzene ring attacking that electrophilic nitrogen. And then what else do I have to do here? Nitrogen can't have 5 bonds, right? So then in the same step, it's going to give up that pair of pi electrons to that oxygen. That's how oxygen ends up with 3 lone pairs on my product. Okay. All right, our next reaction, same idea, still another electrophilic aromatic substitution reaction. All right, but this one puts on an SO3H group. SO3H. All right, this is what's called a sulfonic acid group. Okay, let's draw out the full Lewis structure for this one here. The sulfur is what's bound to our carbon. It's got these 3 oxygens coming off of it. It's actually double bonded to 2 of them, and then a OH. Okay, and this looks really weird, but remember our larger elements, once you get to like row 3 and below, you can have what's called your expanded octet. So sulfur can actually fit all, 2, 4, 6, 8, 10, 12 electrons into its octet here. Okay. In order to have this reaction occur, you're going to use sulfuric acid, but they call it fuming sulfuric acid. Basically, you're just going to boil the crap out of this, and it's the fumes in that mixture that are reacting with your benzene ring. If we take a look at our actual electrophilic species here, we see something similar to what we saw with that nitric acid where we formed that nitrogen dioxide, and that nitrogen in the middle was left with that positive formal charge. Same sort of idea, we form sulfur trioxide, and it has this partial positive charge in the middle, making this our good electrophilic site. So that benzene ring attacks that partial positive charge, giving us our product. Okay, so we'll sort of summarize all of these in a reaction wheel at the end. We got 2 more to do here, 2 more electrophilic addition reactions. These kind of fall under the same umbrella here, called Friedel-Crafts reactions, after the scientists who established them. All right, so the first one would be a Friedel-Crafts alkylation reaction. Okay, where we can take our benzene ring and stick an alkyl group on there. What the heck do I mean by an alkyl group? Yeah, carbons and hydrogens, right? Just some sort of, an ethyl group, a methyl group, a propyl group. All of those are our alkyl groups, right? And we can sort of write this generically as R. Right, some R group here. Okay, so our reagents that we would use for these alkylation reactions would be an alkyl chloride. So whatever our R group is, it needs to have a chlorine on it. And then that same aluminum chloride catalyst that we saw previously. Okay, and so our actual electrophilic species here let's see if we can't figure it out based on what we learned before about these aluminum chloride catalysts here. So I'm just going to take the simplest possible R group that we can have, a methyl group. So chloromethane here. All right. So aluminum's kind of a weird one. If we look on where it is on the periodic table, it's right next to this staircase here, right? Generally speaking, we would treat aluminum as a metal. We think of it as forming these cations with the +3 charge. But being that it's so close to our staircase over here, it's also more convenient sometimes to think about it as being a covalent forming compound, meaning that it's in this compound right here has this incomplete octet. So aluminum is really good at accepting a pair of electrons. And we saw this before when it formed that complex with the halogen. It's going to do the same thing here as well. Okay? The only difference is that carbon is one of those elements that you can actually find with an incomplete octet. So in this case, this aluminum chloride just straight up plucks that chlorine right off of that alkane. All right, and so this leaves us with what as our electrophilic species? Everybody take a second and draw me the product of this reaction here. You see it over and over and over again. What is it? Carbocation. So that's our actual electrophilic species. Again, making a really good electrophile, something with this positive charge here, can very easily accept a pair of electrons from that benzene ring. All right, so let's make sure we got this down. Let's practice this a little bit, looking at actual R groups here. All right, so everybody just take a second and draw me the product of these 3 Friedel-Crafts reactions here. All right, so importantly, when you're drawing your product, right? I have, let's color these carbons here. The carbon that's going to be bound to my ring is the one that contained that halogen on there, contained that chlorine, right? So my carbon 2 is where my halogen was. That's what's going to be bound to my ring. All right. These aren't too bad other than you're creating new carbon-carbon bonds, which is always a little messy. The best double check that you can do is go back and count carbons. Make sure you got the same number of carbons on both sides. Okay, so same thing over here. I need to attach this carbon right here. That's where my carbocation is going to form. Right, so that's what I need to make sure is my new carbon-carbon bond. Okay. Now, I said all that, but if we look at this one here, it turns out that the major product of this reaction, if I'm going to color my carbons, this one's red, this one's blue. My major product of this reaction is actually the same as that first reaction we looked at, where this new carbon-carbon bond is formed between the second carbon in my compound. Why would that be? Yeah, so more stable as a secondary carbocation, but more importantly, what phenomena do we have to watch out for when we have these carbocation intermediates? We haven't talked about it yet this semester, but it was a big sort of pain in the butt thing we had to look out for last semester. Hydride shifts and methyl shifts, right? So the bottom line is yes, in this reaction, the very first step is that chlorine is removed, forming that carbocation, right? But then we're going to see a hydride shift to put that carbocation on the more stable secondary carbon. If we want to draw out our full mechanism for a hydride shift, that's where this hydrogen and its pair of electrons jumps over. So all that to say, because these Friedel-Crafts reactions undergo these, go through these carbocation intermediates, for these Friedel-Crafts alkylations, we're going to say, watch out for hydride shifts. Hydride/methyl shifts. Okay, so let's say that I really wanted to get this primary carbon attached to my ring. I'm not going to use this Friedel-Crafts alkylation reaction because I'm going to see a hydride shift. So we're going to have a different sort of method here. Let's introduce the last of these Friedel-Crafts reactions. These are what are called acylation reactions. Don't hate me. I don't know why we have 1,000 different names for it, but an acyl group we also call what bond? What is this carbon-oxygen double bond? Carbonyl group. So this is just going to be attaching a carbonyl group to that ring. All right, so our product here, again, we're forming a new carbon-carbon bond, but it's specifically to a carbonyl carbon. And there can be whatever on the back end there, but it's specifically that carbonyl carbon that's going to be attached to our ring. and so this is going to be very similar, except for now, instead of just an alkyl halide, we're going to have a chlorine attached to that carbonyl group. We call an acyl chloride, and again, that aluminum chloride catalyst. Okay. Our electrophilic species, just like before, that catalyst is able to remove that chlorine from that compound, leaving us with a carbocation. But now that carbocation is kind of a special carbocation because it's a carbonyl carbon. All right, and one of the things that's special about these carbocations is they will not undergo hydride or methyl shifts. Alright, so if we want to look at a specific reaction here, let's take our benzene. I'm going to react it with an acyl chloride. Alright, everybody take a second and give me my products. Alright, so importantly, I'm going to attach that carbonyl carbon to my benzene ring. And I just got to make sure to include all 1, 2, 3, 4 carbons on the back end, so a total of 5. Boom. Right? It is your carbonyl carbon that's becoming your carbocation, your electrophile in this reaction. All right. Okay, so now let's go back and revisit what we were talking about before. Let's say that I have benzene, and I really want to make propylbenzene. Right? Well, I can't just do my Friedel-Crafts reaction, my Friedel-Crafts alkylation reaction, because instead I will see the hydride shift as my major product. So this isn't going to work for us here, this sort of direct alkylation method. All right, so what can we do instead? Well, first, let's do a Friedel-Crafts acylation reaction. We'll use a 3-carbon acyl halide. right? This attaches my 3 carbons onto my ring in the correct orientation. I'm not attached at carbon 2, I'm attached at carbon 1. Okay, but I still have this carbonyl group on here, right? Well, if we had a way to chop off that carbonyl oxygen, just whoosh, chop it off, that would get us to the product we want. And so indeed, we have this method that we can use to reduce these alkyl groups here, or rather these carbonyl groups, cutting that oxygen completely off. And I don't remember off the top of my head, it uses some metal. Go to my cheat sheet. Here we go, yeah. So we're going to use zinc and HCl. Okay, so if we really want to attach that primary carbon to our ring, rather than taking the alkylation method, this one won't work. So instead we're going to do an acylation, and then we're going to reduce that carbonyl. You can even say fully reduce that carbonyl. Okay, so let's summarize all of this into one sort of reaction wheel here so we can see it all next to each other. We have our benzene ring, and we learned how to put a few different groups on there. If we wanted to put a bromine on the ring, use Br2, and that catalyst, either iron or aluminum tribromide. Same thing with chlorine on our ring, very similar. Again, using that catalyst. Okay. We also talked about these nitration reactions, putting a nitro group on there. Whoops, NO2. Nitric acid and sulfuric acid. Put a sulfonic acid group on there, SO3H, that uses fuming H2SO4. Okay. If we want to put an alkyl group on there, we'll do a Friedel-Crafts alkylation reaction. We just said for these, we got to watch out for hydride and methyl shifts. All right, and then the last one, sort of squeeze it in over here, are the Friedel-Crafts acylation reactions, so ClCOR. And again, that same aluminum catalyst. All right, and then just to kind of keep it, we had one extra step that we could do from our acylation product, which was to treat it with zinc and acid, and that will reduce our carbonyl to just carbons and hydrogens. Okay. We're going to add one more reaction to this wheel here, and this will be the extent of the reactions that we cover for the most part this chapter, and then we're just going to start mixing and matching them. All right. That is that you can actually reduce this nitro group as well to just an amine group. This guy actually has a special name. What do we call a benzene ring with an amine group? Aniline. So we can turn nitrobenzene into aniline, doing something very similar that we were doing with our carbonyl group, where we take zinc under acidic conditions, but then for whatever reason in the second step, you got to follow it up with a strong base. So we have these different aromatic substitution reactions, electrophilic aromatic substitution reactions, where we take a benzene and we swap out one of the hydrogens for one of these new functional groups here. All right, so we're going to just use these reactions over and over again. Now we got our first big pot of reactions that we've learned about for this particular semester. Remember, the best thing that you can do to keep track of all these is to flashcard them. Try to get them in your mind here. You'll be given a reagent bank, but of course you need to be able to recognize it and know what that reagent does. Okay, so just for practice here, here we go. We have a benzene ring. Okay. So I'm going to first hit it with Br2 and aluminum tribromide. All right, and what is that going to put on the ring? Just a bromine, right? Boom, Br. Don't tell me it's Br2. It's definitely not two bromines on there, just one. Okay. Now we're going to start mixing and matching these reactions here. So if I next take this and do one of these nitric acid and H2SO4, what's the new group that I'm putting on the ring? That nitro group. All right, but now that I'm doing this second reaction, the question is, like, where does it go? Does it go in my ortho positions? Does it go in the para positions? Or I'm sorry, the meta positions? Or does it go in the para position? Okay, so it turns out that there's going to be a logic behind which one of these carbons we put this new group on. In this case, one of our major products will be in that para position. All right, but what's going to make this very interesting is we don't have this like one size fits all rule. If I took these same two reactions and I reversed the order, I first did my nitration reaction and then did my bromination reaction afterwards, I would actually get a different product. I would get the meta product. Okay, so we're going to start mixing and matching these reactions to create di-substituted rings. And what we're going to find is the order in which we do these reactions will have an impact on what our product is. Okay? So, we're going to sort of have to take all these different substituents in our benzene and lump them into different groups here. All right? And we've sort of seen this terminology before. Okay, some of our substituents are what are called electron donating groups. All right, so we've seen this when we were talking about our Diels-Alder reactions. An electron donating group is something that's bound to the ring that has a pair of electrons. So for example, phenol would be a good example of a benzene derivative with an electron donating group. All right, so let's draw our resonance structures so we can try to figure out what electron donating groups prefer products-wise, ortho, meta, or para. All right, so what it's going to do is it's going to donate a pair of electrons. That's what an electron donating group does, right? Brings that pair of electrons down to the ring. Okay, can I stop right there? What's wrong? Yeah, that carbon, if I stop right there, that carbon's going to have too many bonds, all right? So this pair of electrons can jump up right here. Okay, so let's draw our first resonance contributor. Now I'm double bonded to my oxygen. Okay, so everybody take a second and make sure that we got all of our formal charges and stuff worked out. Fill in my missing formal charges here. All right, what's missing from here? Do I have a positive charge anywhere? Where? My oxygen. Where's my negative formal charge there? On the carbon that accepted that pair of pi electrons. Okay, so here's one of my resonance contributors, and now I can kind of play this game with this pair of electrons, and I'm going to bounce it around that ring, right? So I'll get another one if this pair of electrons comes down here. If this comes down here, what else has to happen? Can I just leave it like that? No, right? So I'm going to have to kick this pair of pi electrons up onto this carbon. All right, so draw my next resonance contributor here. All right, and see if you can't finish this off and draw the last resonance contributor for this here. right, so same game. I'm going to move this pair of electrons down. That'll be my new pi bond, but I got to kick this pair up onto that carbon. Whoops. All right, so my last resonance contributor here. Okay, so if I have an electron donating group on my benzene ring, it can donate that pair of electrons, and that's what we've illustrated through these resonance structures here, right? Remember, like, it's not one resonance structure that's true at a time. They're kind of all true at the same time, all right? It's one of the weird magical things about resonance. Okay, so we're going to try to use this to figure out where the next group is going to go. Let's remind ourselves of two important things here. In these electrophilic aromatic substitution reactions, what is it that's playing the role of the nucleophile? If we look up at one of our reactions here, let's go to our just generic mechanism that we had from the beginning. What's playing the role of the nucleophile? Benzene or the other thing? Benzene. Benzene's the nucleophile in our reaction, right? Okay, so in our EAS reactions, benzene is the nucleophile. And a good nucleophile is what? Electron rich or electron poor? Well, let's go back up here to these resonance structures. When we have this electron donating group, it's donating electrons to this ring. It's actually going to make benzene an even better nucleophile, right? Because it's putting even more electrons into that ring. But it's specifically making two of these positions about that ring better nucleophiles. What are those two positions? Yeah, where do my carbanion go? Notice how the only positions in my carbanion are these two ortho positions and this para position at the very bottom. That pair of electrons skips over that meta position, right? We never have a carbanion here on that meta position, okay? So that electron donating group is going to make that benzene ring even more electron rich, but specifically at those two positions, okay? So good nucleophile is electron rich, and we can say specifically at the ortho para positions. Okay, so these electron donating groups, as we sort of illustrated using resonance here, they will direct incoming substituents to either the ortho or the para position. So we call these ortho para directors. Okay, so you maybe can see where we're going here. Now we're going to look at what happens when we have electron withdrawing groups. And, punchline, it's going to be the exact opposite of what we saw with our electron donating groups. But let's kind of illustrate that. So now let's look at some electron withdrawing groups. We talked about how carbonyl carbons are electron withdrawing groups, and that's true. The one best electron withdrawing group that you could possibly have is that fancy nitro group that we introduced. And in electron withdrawing groups, are they going to add electrons to the ring or take electrons away? As the name implies, it's going to withdraw electrons from that group, right? So if I'm going to do my resonance structure, I'm going to take a pair of electrons out of that ring. That nitrogen is able to pull that electron density onto itself. Okay? I can't stop here though, because otherwise that nitrogen will have too many bonds. So if it's going to take a pair of electrons from that ring, it's got to kick that pi bond onto that oxygen. All right, so everybody take a second and draw me my resonance contributor that we would get here. So my oxygen, now I have to add that pair of electrons and that negative charge. My nitrogen now has that extra bond with carbon in the ring, so it still keeps its positive formal charge. And then what am I missing? Yeah, which one? The one that got the pair of electrons taken from it, right? Okay, so now we can just play this game where we're going to bounce this positive charge around this ring using resonance. So another resonance contributor I can draw with that pair of electrons moving over. So now my carbocation is down in this para position. And then last step again, just bouncing that positive charge around that ring. Cool. Okay, so I have this electron withdrawing groups. Now it's going to take electron density out of the ring, right? So are these electron withdrawing groups, are they going to make benzene a better or a worse nucleophile? Who thinks a better nucleophile? Who thinks a worse nucleophile? Yes, so it will make benzene a worse nucleophile. These reactions with these electron withdrawing groups will be slower than you would if you just had benzene by itself or if you had an electron donating group, right? You're taking density out of that ring, okay? So let's just say electron withdrawing groups. Make our benzene a worse nucleophile. All right, but there are specifically two positions up here that are absolutely going to be trash nucleophiles according to our resonance structures. And which two are those? Where do I see that positive charge being bounced from? The ortho to the para, right? So these are what we call, these electron withdrawing groups are what we call meta-directing groups. But it's not so much that they stabilize the meta position or they add electron density to the meta position. They just make the ortho and the para positions terrible nucleophiles, right? They're taking electron density specifically away from those ortho para positions, right? So electron withdrawing groups make benzene and works nucleophile specifically at the ortho and para positions. Okay, so then let's take a look at two reactions here, side by side. Let's see if we can't guess. I'm going to take benzene, regular old benzene. Let me copy and paste. All right, and first I'm going to treat it with nitric acid and sulfuric acid, and then in a second step I'm going to treat it with chlorine and aluminum chloride. All right, and I want you to tell me what my products of these would be. All right, so that first step puts a nitro group on there. That second step is going to put what type of group on there? Chlorine. And specifically, where is that chlorine going to go? Is it orthopara or meta? Okay, yeah. Importantly, the nitro is what's directing where that incoming group goes. The chlorine doesn't get to decide where it goes. The nitro group, the thing that's already on the ring, is going to be directing the incoming substituent. And since this is a meta-directing group, an electron withdrawing group, that chlorine is going to go in the meta position. All right, so then let's take these same two reactions, but we're going to reverse the order. Now we're going to put the chloro group on first and the nitro group on second. So now the first thing to be put on that ring is going to be that chlorine. These halogens have these pair of electrons, right? So this is the easiest feature that you can spy of one of these electron donating groups, is if it has a pair of electrons directly next door. Okay? So does that make this orthopara or meta-directing? Orthopara. So we're going to get a mix of the ortho and the para products. Let me make this a little bit smaller. Okay. Okay, so let's think real quick about, so we get both the ortho and the para products because again, that chloro group, which was on there first, is an ortho-para director. Okay. It turns out that your distribution of products that you would get here would be about 66% ortho to 33% para. All right, so we get twice as much of the ortho product as we do the para product. Why might that be? Let's take our chlorobenzene and let's look closely. What is this position right here? The ortho, and then this position we don't see any addition to, that's the meta position. And what about this one at the bottom? The para position, again going around the ring, we don't see anything here, but we get back up here and what's this one? Also ortho. How many ortho positions do we have? 2. And how many para positions do we have? Just 1. So it's just kind of a numbers game, right? If you got nitro groups being attached randomly here, there's twice as much of a chance of being attached to the ortho as to the para. Okay? All right, so why do we see the distribution that we do? We have twice as many ortho positions as para positions. Okay, but this chloro group is a rather small substituent here. We're going to do the same sort of game here. But now I'm going to take this benzene ring here. It's got this big alkyl group on there. Okay, we'll talk a little bit more about alkyl groups for right now. I know there's no lone pairs on them, but you're just going to trust me that these alkyl groups are ortho para directors. So if we do our nitration reaction, we're going to have a nitro, 2 different products, one in the ortho position, one in the para position. Okay, but if we look at the distribution of products here, now our ortho is only about 10% of our product distribution, with 90% in that para position. Okay, so different than what we saw for chlorine. Why do we think that might be? So stable, but why more stable? Two big groups, exactly. What do we call that when we, two big groups that don't like interacting with one another, we call that steric hindrance, right? So when we have a really large substituent already on the group, the effective sterics take over and it will direct it to the far side, okay? So with larger substituents, all right, and we gotta sort of make a cutoff here. We're gonna say 3 carbons or more. Okay, so if you have a larger substituent, something with 3 or more carbons, sterics will dominate, and the para will be the major product. Cool. All right, we will sort of pick up with this next time. You can see, again, sort of hopefully it makes a little bit more sense what I was saying. We got these 6 reactions that we learned about, these electrophilic aromatic substitution reactions, and now we're mixing and matching them, right? So what we'll start with next time is throwing each one of these groups into the category of either ortho-para-directing or meta-directing. Okay, so we'll go one by one with this list that we've created up here.